What if the universe is trying to talk to us? Picture this: vast, drifting clouds of gas floating silently between the stars, where no human eye has ever seen, no spacecraft has ever traveled. And yet they're broadcasting signals, strange, pulsing whispers of energy that cut through the darkness, reaching out like cosmic Morse code. Scientists have trained their most powerful telescopes on these interstellar clouds, only to find patterns that defy explanation, rhythms that don't match any known natural phenomenon, frequencies that seem almost intentional. It's as if the universe itself is hiding messages in plain sight, waiting for us to decipher them. This isn't science fiction. These are real, documented signals, enigmas wrapped in stardust scattered across the galaxy. Some repeat at precise intervals like celestial clockwork. Others flicker just once and vanish, leaving astronomers scrambling for answers. Where do they come from? What could possibly generate such precise, mysterious bursts of energy in the emptiness between stars? The closer we look, the more questions arise. Could these be the echoes of alien technology, the remnants of long-dead civilizations, or something even stranger? Or are we witnessing natural processes so extraordinary they rewrite everything we thought we knew about the cosmos? Today, we're diving deep into 25 of the most perplexing signals ever detected, each one a cosmic riddle begging to be solved. From haunting radio waves that loop endlessly across the void to sudden, brilliant flares that vanish without a trace, these aren't just anomalies. They're clues, pieces of a puzzle that could reshape our understanding of the universe itself. So let's unravel these interstellar mysteries together, one signal at a time. By the end, you might just find yourself staring at the night sky, wondering what else is out there, quietly calling into the dark. The WOW signal remains one of the most tantalizing mysteries in the history of astronomy, a single, powerful burst of radio waves that lasted just 72 seconds, then vanished forever. On August 15, 1977, a telescope at Ohio State University's Big Ear Radio Observatory picked up a signal so intense, the astronomer who discovered it scribbled "WOW" in red ink on the printout. That single word gave the phenomenon its name, and nearly 50 years later, we still haven't found a satisfying explanation. What made this signal so extraordinary wasn't just its strength, it was the way it precisely matched the expected signature of an artificial transmission. It appeared to originate near the constellation Sagittarius, blaring at a frequency of 1,420 MHz, a range scientists call the water hole, because it's where hydrogen and hydroxyl molecules emit natural radio waves. This region of the spectrum is eerily quiet, making it a prime spot for interstellar communication, and that's why the WOW signal's appearance here sent shockwaves through the scientific community. Theories range from plausible to mind-bending. Some argue it could have been a natural event, like a comet's hydrogen emission or a bizarre stellar flare. But no known cosmic phenomenon fits the signal's unique profile. It was narrow, focused, and unlike any random burst ever recorded. Others suggest it might have been a one-time transmission from an alien civilization, perhaps a beacon briefly sweeping past Earth before disappearing into the void. What's especially haunting is that despite decades of searching, we've never detected anything like it again. Was it a cosmic fluke, a fleeting call from another intelligence? Or something beyond our current understanding of physics? The WOW signal's silence since that night only deepens the mystery and keeps us listening. Decades after that fateful night in 1977, the WOW signal continues to defy explanation, but not for lack of trying. In 2020, a team of researchers proposed a bold new theory. What if the signal wasn't alien at all, but the result of hydrogen clouds drifting through space? The idea hinges on how these vast interstellar structures can amplify and distort radio waves, potentially creating brief, intense bursts that mimic artificial signals. At first glance, it's a compelling natural explanation until you dig deeper. The hydrogen cloud theory has one glaring problem: timing. The WOW signal's 72-second duration and sudden disappearance don't align with how these cosmic clouds behave. Natural radio bursts from hydrogen tend to linger or repeat, not vanish without a trace. Even more puzzling, follow-up observations of the same patch of sky found no trace of the dense gas required to produce such a signal. It's like hearing a gunshot in an empty room: no gun, no shooter, just the echo of something inexplicable. Meanwhile, other scientists have combed through decades of radio telescope data, searching for anything remotely similar. They've found nothing. Not a single signal matches the WOW's unique fingerprint, its precise frequency, its razor-sharp intensity, its eerie silence afterward. Even human-made interference, like satellites or military transmissions, fails to explain it. No known technology in the 1970s could have produced such a clean, focused burst from that region of space. So where does that leave us? The WOW signal stubbornly refuses to fit into any neat scientific box. It's too deliberate to be random noise, too fleeting to study, and too perfect to ignore. Whether it was a 1 in a trillion cosmic coincidence or a deliberate broadcast lost to time, one thing's certain: it's a reminder of how little we truly understand about the universe's hidden symphony. And perhaps that's the real message of the WOW signal. The cosmos still holds secrets we're only beginning to whisper about. If the WOW signal was a fleeting whisper, then the Lorimer Burst was a scream, a violent, one-off explosion of radio waves so powerful it rewrote the rules of astrophysics. In 2007, astrophysicist Duncan Lorimer and his student David Narkevic were sifting through old data from the Parkes Radio Telescope in Australia when they stumbled upon something bizarre: a 5-millisecond blast of energy so intense it outshone entire galaxies. This wasn't just noise, it was a cosmic detonation, unleashing more energy in that blink of an eye than our sun emits in 30,000 years, and then it was gone. What made the Lorimer Burst so revolutionary wasn't just its raw power, it was how utterly it defied explanation. Most radio signals from space have clear origins: pulsars spinning like lighthouses, supernova scattering debris, black holes shredding stars. But this came from nowhere: no visible source, no lingering afterglow, no repeating pattern. Just a single, staggering spike in the data, as if the universe had flicked a switch. Astronomers were left with two unsettling possibilities: either they discovered a brand new class of cosmic cataclysm, or something even stranger was at play. The implications sent shockwaves through the scientific community. Traditional models couldn't account for such a brief, energetic event without a trace. Theories exploded like fireworks: colliding neutron stars, evaporating black holes, primordial cosmic strings snapping. Each idea crumbled under scrutiny, leaving researchers grasping at the edges of known physics. The Lorimer Burst forced them to confront an uncomfortable truth: the cosmos might be hiding phenomena beyond even their wildest theories. And then came the real twist. Years later, astronomers realized this wasn't a fluke. The Lorimer Burst was the first of many, dozens of similar signals now called fast radio bursts, or FRB, each one a microsecond mystery echoing across billions of light years. Some repeat like clockwork, others vanish without a trace, but that first burst, that 5-millisecond enigma, remains the Rosetta Stone of the FRB phenomenon: a single day to point that cracked open an entirely new field of astronomy. Without it, we might still be oblivious to these cosmic fireworks, flickering in the dark like signals from a universe far stranger than we ever imagined. But then came a discovery that shattered expectations: repeating fast radio bursts, signals that didn't just flash once and vanish but returned again and again like a cosmic heartbeat. The first of these, FRB 121102, changed everything when it was detected in 2012. Unlike the Lorimer Burst's fleeting violence, this signal pulsed back to life months later, and then kept pulsing, irregular but undeniable, like a radio station tuning in and out across the universe. Suddenly, astronomers weren't just chasing ghosts, they had a target. The repeating nature of FRB 121102 ruled out catastrophic one-time events like colliding neutron stars. Instead, it pointed to something persistent, a cosmic engine capable of generating these bursts over and over. Magnetas quickly became the leading suspect. These ultra-dense, highly magnetized neutron stars spin wildly, their magnetic fields so intense they could snap and release massive energy bursts. Picture a spinning top wrapped in a million rubber bands. When one finally snaps, it sends a shockwave rippling outward. Some magnetas even emit regular X-ray pulses, making them a plausible match for repeating FRBs. Yet even magnetas struggle to explain everything. FRB 121102's bursts aren't just repetitive, they're chaotic with no strict rhythm. Some arrive in clusters, others go silent for months. Then there's the location. This FRB hails from a dwarf galaxy 3 billion light-years away, a strange environment packed with star-forming gas, hardly the tidy neighborhood you'd expect for a lone magneta. Could these bursts instead come from a magneta orbiting a black hole, its magnetic fields twisted and amplified by the black hole's gravity? Or perhaps they're the death cries of stars being shredded in dense stellar nurseries. And then there's the idea that refuses to die: alien technology. The Harvard astronomer Avi Loeb famously suggested that FRBs could be leakage from powerful interstellar beacons, like cosmic lighthouses guiding ships across galaxies. It's a fringe theory, but the sheer precision of some bursts, like a focused radio beam sweeping past Earth, makes it hard to dismiss entirely. After all, if humans accidentally leak radio waves into space from TV broadcasts, could another civilization be doing the same, but deliberately? What's undeniable is that repeating FRBs have cracked open a new window into the universe's most extreme physics. Each burst is a fingerprint carrying clues about the magnetic storms, gravitational warps, or, who knows, maybe even the technologies that created them. And with every new detection, the mystery only deepens, because if these signals are natural, why do some repeat while others don't? And if they're not, well, that's a question we're only beginning to dare ask. Just when we thought we'd heard it all, in late 2020, astronomers detected something extraordinary: a narrowband radio signal, clocking in at 982 MHz, emanating from the closest star system to our own, Proxima Centauri. Dubbed BLC-1, this signal sent shockwaves through the scientific community because it ticked every box for an artificial transmission. It was focused, drifting in frequency, just as a signal from a moving planet would, and most tantalizingly, it originated from a star known to host at least 2 planets, one of which sits squarely in the habitable zone. For a brief, electrifying moment, it seemed like humanity might have its first concrete evidence of extraterrestrial technology. The Breakthrough Listen project, which discovered the signal, was cautious but hopeful. They'd spent years sifting through cosmic noise, filtering out human-made interference, and BLC-1 passed every initial test. Unlike the chaotic bursts of fast radio bursts or the static hiss of natural radio sources, this was a clean, narrow-band signal, exactly the kind an intelligent civilization might produce. The fact that it came from our nearest stellar neighbor, just 4.2 light-years away, made it all the more compelling. Imagine the implications. If life had arisen there so close, what did that say about its prevalence across the galaxy? But the excitement was short-lived. After months of painstaking analysis, the truth emerged: BLC-1 was almost certainly human-made. The telltale signs were subtle but damning. The signal's frequency drift didn't perfectly match Proxima Centauri's motion, and further scrutiny revealed similar transmissions popping up elsewhere in the data, all traceable to Earth-based electronics. The final nail in the coffin: the signal disappeared when astronomers pointed their telescopes away from Proxima Centauri, but reappeared when they looked back, behavior consistent with interference rather than a genuine cosmic source. Yet BLC-1's legacy isn't one of disappointment, it's a masterclass in how careful the search for extraterrestrial intelligence must be. The signal fooled some of the best instruments and brightest minds precisely because it was so convincingly artificial. It's a reminder that the universe is full of natural oddities, and human technology is shockingly good at mimicking them, but it's also proof that our methods are improving. Every false alarm like BLC-1 sharpens our tools, refines our filters, and brings us closer to the day when we just might find the real thing. Because if a signal this convincing could emerge from our own backyard, what wonders might still be hiding in the depths of space, waiting for us to listen? Among the gallery of cosmic mysteries, few are as quietly unsettling as signal SHB-02+14a. Detected in 2003 by the SETI at Home project, which harnessed the idle processing power of millions of personal computers worldwide. This faint, flickering signal didn't scream for attention like the wow signal or explode across the cosmos like fast radio bursts. Instead, it whispered, a delicate, repeating pulse at a frequency of 1,420 MHz, the same eerily strategic, waterhole frequency as the wow signal, appearing not once, not twice, but 5 separate times over several years. What set this signal apart wasn't raw power, but persistence. Most cosmic noise fades into the background after a single observation. SHB-02+14 kept coming back. Even more baffling was its origin. The signal seemed to emanate from a patch of space near the constellation Pisces, a region so devoid of stars, planets, or even dense gas clouds that astronomers initially assumed it was empty. No pulsars, no quasars, just the void. So what could possibly be broadcasting from a cosmic desert? Theories split into two camps. Skeptics argued it was nothing more than random interference, perhaps a glitch in one of the thousands of home computers processing SETI data. After all, the signal was weak, drifting slightly in frequency each time it appeared, behavior more consistent with electronic noise than a deliberate transmission. But the other camp saw something far more intriguing. The signal's frequency drift wasn't chaotic. It followed a precise pattern, as if the source were moving in a slow, predictable orbit. That detail sent shivers down spines. If the signal originated from a planet orbiting a star, its motion could explain the drift. Yet no star exists where the signal seems to originate. Unless, of course, the star is too faint for our telescopes to see, or the source isn't a star at all. The implications spiral outward from there. Could this be a rogue planet, untethered from any sun, carrying some ancient beacon through the darkness? A derelict alien probe, silently adrift between the stars? Almost unnerving of all, a transmission deliberately aimed at us from a location designed to be inconspicuous. The silence since 2003 hasn't helped. SHB-02+14 remains a ghost in the data, too strange to dismiss but too faint to confirm. It lingers in the archives like a half-heard secret, daring us to listen closer, if only it would speak again. In the summer of 2015, a Russian radio telescope picked up something extraordinary, a strong, narrowband signal pulsing from a star almost identical to our own. HD 164595, located 94 light-years away in the constellation Hercules, isn't just any star. It's a near twin of the Sun, slightly older but with the same size and temperature. And for a brief moment, it seemed to be broadcasting. The signal, detected by the Rattan 600 telescope, lasted just 2 seconds, but that was enough to send astronomers into a frenzy. Here was a sun-like star, a prime candidate for hosting life, emitting a signal that matched no known natural phenomenon. Was this finally the moment we'd all been waiting for? At first glance, the signal had all the hallmarks of an artificial transmission. It was focused, appearing at a frequency of 11 GHz, a range often used for satellite communications here on Earth. Even more intriguing, calculations suggested the source would have required immense power to reach us across interstellar space. If it was a deliberate broadcast, the civilization behind it would need energy equivalent to harnessing the entire output of their star. That level of technological advancement is mind-bending, but not impossible for a hypothetical Kardashev Type II civilization, one capable of harnessing the energy of its solar system. Yet, as with all great cosmic mysteries, the devil's in the details, natural explanations quickly emerged. One compelling theory involves cosmic microlensing, a phenomenon where a massive object, like a wandering planet or a dense star, bends and amplifies background radio waves as it passes in front of them. Picture a magnifying glass floating in space, briefly focusing distant radio noise into a sharp, artificial-looking spike. HD 164595 sits in a crowded region of the Milky Way, making such lensing events statistically plausible. But here's where things get thorny. Microlensing typically produces signals that drift in frequency as the lensing object moves. The HD 164595 signal didn't drift. It was clean, stable, almost too precise for a natural explanation. And then there's the star itself. Unlike Proxima Centauri's red dwarf flares or the chaotic environs of magnetar, this was a calm, mature star, exactly the kind we'd expect to host stable planetary systems. If the signal wasn't microlensing, what else could it be? Military radar bouncing off space debris, a glitch in the telescope's electronics, or something far more profound? The truth is, we may never know. Despite exhaustive follow-up observations, the signal never repeated. It remains a single tantalizing blip in the data, a cosmic Rorschach test. To some, it's proof we're not alone. To others, it's just another reminder of how little we understand about the universe's natural radio symphony. But perhaps the most fascinating part of the HD 164595 mystery isn't the signal itself, it's what it represents. Every time we point our telescopes at the stars, we're gambling. We might find nothing, we might find noise, or we might stumble upon a signal so strange it forces us to rewrite the rules. And that's why we keep listening. Some cosmic mysteries don't come as bursts of static or pulsing radio waves, they arrive as shadows. In 2015, astronomers noticed something bizarre happening to a star 1,400 light-years away. KIC 8462852, better known as Tabby's star after its discoverer Tabetha Boötes, wasn't behaving like any other star in the galaxy. Instead of shining steadily, it flickered, sometimes dimming by as much as 22% before snapping back to brightness. These weren't the gentle, predictable dips caused by orbiting planets. They were erratic, asymmetrical, and utterly inexplicable. And for a brief, electrifying moment, scientists seriously considered the possibility that we might be looking at something never seen before, an alien megastructure. The leading natural explanation involved swarms of cosmic dust. Maybe, researchers thought, vast clouds of debris left over from planetary collisions or the remnants of a shattered moon were drifting in front of the star, blocking its light in unpredictable ways. But there was a problem. Dust scatters certain wavelengths of light, and Tabby's star's dimming didn't match that pattern. It faded almost uniformly across all colors, as if something solid and massive were passing in front of it. That's when the wilder theories took flight. Could this be evidence of a Dyson swarm, a hypothetical superstructure built by an advanced civilization to harvest a star's energy? Imagine millions of solar panels orbiting a sun, catching its light and casting deliberate shadows into space. The idea wasn't just science fiction. It was a testable hypothesis, and for once, astronomers couldn't immediately rule it out. Yet the universe loves a good twist. Over years of observation, the dust theory gained traction, but not ordinary dust. Instead, scientists proposed an extraordinary culprit, microscopic debris from the star itself. Tabby's star is what's called an F-type star, hotter and more massive than our Sun. and some researchers believe it might be devouring planets or comets, belching out vast clouds of fine particles that clump and disperse erratically. These clouds could explain the star's bizarre dimming without invoking alien megaprojects. Still, the case isn't closed. Unlike the predictable orbits of planets or the steady haze of interstellar dust, Tabby's star's behavior remains stubbornly irregular. Some dips in brightness last days, others stretch for years. No single natural phenomenon fully explains the chaos. What makes Tabby's star so captivating isn't just the lingering question of its dimming, it's the door it kicked open in astronomy. Before 2015, no one was systematically looking for stars with strange, irregular light patterns. Now, thanks to this one cosmic anomaly, astronomers have identified dozens of other dipper stars, each with its own unique flickers and shadows. Some are likely explained by dust or stellar activity, but others, well, they're still keeping their secrets, and that's the real lesson of Tabby's star. Sometimes the most profound discoveries aren't answers, they're questions we didn't even know to ask. Whether it's dust, debris, or something beyond our imagination, this star reminds us that the universe is still writing its rulebook and we're only on the first page. In the vast expanse of the cosmos, few things spark the imagination like the idea of a signal from another galaxy, especially when that galaxy is Andromeda, our Milky Way's closest neighbor. In 2015, researchers with the SETI Institute detected something that sent a jolt of excitement through the scientific community, a narrowband radio signal pulsing at 6.6 GHz, seemingly originating from the heart of Andromeda. The implications were staggering. At 2.5 million light-years away, Andromeda is the most distant source ever scanned for signs of intelligence. If this signal was artificial, it would mean confronting the possibility of a civilization so advanced, its transmissions could cross the intergalactic void. The signal stood out for its precision. Unlike the chaotic bursts of natural cosmic phenomena, this was a clean, concentrated emission, exactly the kind of signature you'd expect from a deliberate transmission. It lasted just a few minutes before vanishing, but that was long enough to ignite speculation. Some theorized it might be a beacon, a deliberate call across the gulf between galaxies. Others wondered if it could be leakage from some unimaginable Andromedan technology, perhaps the equivalent of our own early radio broadcasts, but amplified across millions of years of advancement. The mere fact that we could detect it at all suggested a level of engineering far beyond anything humanity has achieved. But as with so many cosmic mysteries, the truth was far more mundane. Further analysis revealed the culprit a satellite, not an alien satellite, not some relic of intergalactic exploration, but an ordinary, human-made communication satellite drifting through Earth's orbit. The signal's frequency matched known satellite bands, and its apparent origin in Andromeda was an illusion caused by the way radio waves can bounce and refract in the upper atmosphere. What seemed like a message from another galaxy was in fact a cosmic case of mistaken identity. Yet the Andromeda signal wasn't a failure, it was a masterclass in scientific rigor. The fact that researchers could trace it back to a satellite, ruling out extraterrestrial origins with meticulous precision, speaks to how far SETI has come. Early searchers might have chased ghosts for decades, but modern techniques allow astronomers to filter out interference with astonishing accuracy. That's progress. And it's a reminder of how rare and precious a genuine signal from beyond our solar system would be. The universe is vast and the noise is endless, but somewhere in that noise there might still be a signal waiting, one that won't be so easily explained away. Until then, every false positive like the Andromeda signal sharpens our tools and hones our patience, because if we ever do hear from Andromeda, we'll need to be absolutely sure it's not just another satellite passing overhead. In 2017, astronomers at the Arecibo Observatory turned their attention to Ross 128, a quiet red dwarf star just 11 light-years away. What they found sent ripples through the scientific community. strange, repeating radio flares unlike anything seen from this type of star before. At first glance, the flares seemed like routine stellar tantrums. Red dwarfs are notorious for their violent magnetic outbursts. But closer inspection revealed peculiarities that refused to fit the usual script. The flares pulsed at frequencies typically associated with human-made satellites, and their patterns didn't match the chaotic bursts expected from a star's natural activity. For a brief, electrifying window, it seemed like Ross 128 might be hiding something far more intriguing than solar storms. The initial explanation pointed to stellar flares, explosions of energy triggered by tangled magnetic fields. Ross 128, like many red dwarfs, is prone to such eruptions which can bathe nearby planets in deadly radiation. But the more researchers studied the signal, the less this theory held water. Solar flares usually scatter radio waves across a wide range of frequencies, yet these emissions were narrowly focused, almost like a laser. Even stranger, the signal drifted in frequency over time, mimicking the Doppler shift you'd expect from a moving transmitter. That detail sparked whispers of a radical possibility. Could this be interference from a rogue satellite, or something even more extraordinary? The debate took a surreal turn when researchers realized no known human-made objects were orbiting in Ross 128's direction at the time. If the flares weren't from the star itself, and they weren't from Earth, what was left? The unsettling answer: no natural explanation fully accounted for the signal's oddities. Some astronomers floated the idea of an undiscovered exoplanet with an unusually active magnetosphere, a cosmic generator spewing structured radio waves into space. Others dared to suggest the unthinkable, that an advanced civilization might be leaking transmissions, either deliberately or as a byproduct of technology. Yet as quickly as the mystery flared, it dimmed. Follow-up observations failed to detect a repeat of the signal, leaving researchers with only theories and a lingering sense of unease. The flares from Ross 128 remain an open case, a tantalizing maybe in the search for cosmic anomalies. They remind us that even our closest stellar neighbors can harbor secrets, and that sometimes the most mundane explanations still leave gaps wide enough for wonder to slip through. After all, if a star barely a stone's throw from Earth can defy expectations, what else might be hiding in plain sight, waiting for us to notice? In the swirling sea of fast radio bursts, one signal stands apart, a cosmic metronome beating with eerie precision. Discovered in 2018 by the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, this repeating burst, dubbed FRB 1812-02, doesn't just flash and fade like its cousins. It cycles every 16.35 days like clockwork. It erupts in a flurry of radio pulses for roughly 4 days before falling silent for another 12. This isn't randomness, it's rhythm, and that rhythm might hold the key to unraveling one of the universe's greatest mysteries, the invisible webs of gas that stretch between galaxies. What makes the CHIME repeater so revolutionary isn't just its predictability, it's what the signal carries. As these bursts race through space, they pass through vast clouds of interstellar gas, which leave faint fingerprints on the radio waves. Think of it like sunlight filtering through stained glass. The colors that emerge tell you something about the glass itself. Similarly, distortions in the repeater's signal reveal the density, temperature, and even the magnetic fields of the gas clouds it traverses. CHIME's unique design allows it to map these distortions with unprecedented clarity, turning each burst into a sonar ping echoing through the cosmic deep. But the real magic lies in the repeater's 16-day cycle. That cadence points to an orbiting source, perhaps a neutron star swinging around a companion star or black hole, its bursts flaring like a lighthouse beam whenever it faces Earth. As that orbit twists through different pockets of interstellar gas, the signal's distortions shift slightly, allowing astronomers to construct a three-dimensional map of the otherwise invisible material between galaxies. It's like tracing the outline of a shadow in the dark, one burst at a time. Of course, not all the gas is passive. Some clouds are turbulent, their magnetic fields scrambling the signal in ways that hint at violent stellar explosions or the gravitational pull of dark matter. Others are eerily smooth, suggesting regions where the universe's primordial gas remains untouched since the dawn of time. The chime repeater isn't just a mystery, it's a tool. A cosmic probe letting us see the unseen, one 16-day heartbeat at a time. And with each cycle, it whispers secrets about the universe's hidden architecture, proving that sometimes the most profound discoveries aren't just about the signal, but what the signal passes through on its way to us. Deep in the infrared haze of the Milky Way, something glows where nothing should. Glimpse 01 isn't a star, a planet, or even a nebula, it's a ghost. A patch of space in the constellation Aquila, roughly 3,000 light-years away, that radiates infrared light with no visible source. Discovered by NASA's Spitzer Space Telescope, this strange emission defies all expectations. Normally, infrared signals come from warm dust or young stars still shrouded in their birth clouds. But Glimpse 01 flickers alone in the void, a cosmic flashlight with no battery. At first, astronomers assumed it must be a protostar, a star in its earliest stages of formation, hidden behind thick curtains of dust. But when they trained other telescopes on the region, searching for the telltale heat or gravitational tug of a newborn star, they found nothing. The glow persisted, stubbornly sourceless. That's when the theories took a turn toward the extraordinary. One possibility involves a rogue planet, a world torn from its star, drifting through interstellar space, its atmosphere heated by internal radioactivity or tidal forces. Yet even the most extreme rogue planets shouldn't produce infrared signatures this bright, unless, of course, we've stumbled upon something far stranger. Another hypothesis points to dark matter annihilation, a process where hypothetical particles collide and release energy. While unproven, certain dark matter models predict such events could produce faint infrared glows in empty space. Glimpse 01 sits in a region where dark matter is thought to clump, making this idea tantalizing if speculative. Then there's the wild card, a neutron star's dark twin. Some theorize that certain collapsed stellar remnants, like quark stars or strange matter objects, might emit unusual infrared radiation without the typical X-ray or radio pulses we associate with neutron stars. But perhaps the most haunting possibility is that we're seeing the aftermath of a cataclysm, a star that died in a way we've never witnessed. Imagine a supernova so faint, so obscured by dust, that only its cooling debris remains visible as an infrared whisper. Or a black hole's stealthy feast, consuming a cloud of gas so slowly that it emits no dramatic flares, just a steady, eerie warmth. Glimpse 01 refuses to fit into any neat category. It's not quite a star, not quite a planet, and not quite anything else we've catalogued, and that's what makes it so fascinating. In a universe where we've mapped billions of galaxies and classified countless celestial objects, here's a patch of sky that still holds secrets. A reminder that for all our telescopes and algorithms, the cosmos keeps a few cards close to its chest. Whether it's a new kind of object, a shadow of dark matter, or something beyond our current physics, one thing's certain: Glimpse 01 isn't just a mystery. It's an invitation. Keep looking. There's more out there than we've ever dreamed. The cosmos is full of explosions, supernova blasting apart stars, black holes shredding matter into fireworks of light. But in 2018, astronomers witnessed something that didn't just break the rules, it ignored them entirely. The Vela Jr. anomaly wasn't your average gamma-ray burst. Detected by NASA's Fermi telescope, this eruption of high-energy radiation should have been accompanied by a blinding optical counterpart, the visible light signature of a dying star or colliding neutron stars. Instead, there was nothing, just a silent, invisible detonation in the void, as if the universe had flipped a switch no one knew existed. What makes this anomaly so perplexing is where it came from. The burst originated near the Vela Jr. supernova remnant, a ghostly cloud of gas and dust left behind by a stellar explosion roughly 1100 years ago. Gamma-ray bursts from supernova remnants aren't unheard of, but they always leave traces, expanding shockwaves, glowing debris, something to mark the violence that just occurred. Vela Jr. offered none of that. It was like hearing a gunshot in an empty room and finding no bullet, no gun, not even an echo. Theories scramble to explain the impossible. One possibility involves a failed supernova, a star collapsing directly into a black hole without the usual fireworks. Imagine a building imploding so perfectly, not a single brick falls outward. But even that wouldn't account for the burst's sheer energy. Then there's the idea of a neutron-star merger hidden behind thick interstellar dust, the optical light smothered before it could reach us. Yet follow-up observations found no dust cloud dense enough to cloak such an event. The most tantalizing explanation, a new kind of cosmic cataclysm altogether. Some researchers speculate that certain supermassive stars, when they die, might produce gamma rays through processes we've never observed, like magnetic fields twisting into knots of pure energy, releasing a burst without the messy aftermath. Others wonder if this was the death cry of a magnetar, a neutron star with a magnetic field so intense it can rip space-time itself. But here's the real kicker: Vela Jr. isn't alone. Since 2018, astronomers have spotted a handful of similar, orphan gamma-ray bursts, flashes without a source. They're rare, elusive, and frustratingly inconsistent, suggesting our current models of stellar death are missing entire chapters. Whether it's hidden physics, unknown celestial objects, or something even stranger, one thing's clear: the universe still has explosions up its sleeve we haven't begun to understand. And that's what makes the Vela Jr. anomaly so thrilling. It's not just a mystery, it's a preview, a glimpse into the cosmic phenomena we haven't even named yet. Somewhere beyond the edges of our observable universe, something massive is pulling. That's the startling implication behind the dark flow signal, a peculiar ripple in the cosmic microwave background that suggests entire clusters of galaxies are moving in unison, as if tugged by an invisible hand. Discovered in 2008 by analyzing data from NASA's Wilkinson microwave anisotropy probe, this subtle pattern defies everything we know about cosmic motion. The universe expands evenly in all directions, like rising dough, except here, where hundreds of galaxy clusters stream toward a single point in space at speeds approaching 1,000 kilometers per second. The culprit no one knows, but the leading theory is as radical as it gets: our universe might be feeling the gravitational pull of another. The signal itself hides in the faint afterglow of the Big Bang, the cosmic microwave background radiation that permeates all of space. By studying how this radiation scatters off moving galaxy clusters, scientists detected an unexpected Doppler shift, a telltale sign that these clusters aren't just drifting randomly. They're marching. What's unnerving is the scale. This motion isn't localized to a few galaxies. It spans billions of light years, implicating structures so vast they lie beyond our cosmological horizon. That means whatever's causing the dark flow isn't just outside our galaxy or even our galactic supercluster. It's outside the observable universe entirely. That's where multiverse theories enter the picture. Some cosmologists suggest the flow could be evidence of a neighboring universe brushing against ours, its gravity leaking through the fabric of space-time like magnetism through a wall. Imagine two soap bubbles floating in a void where they touch. Their surfaces might ripple, creating distortions visible from within. If true, the dark flow signal would be our first empirical hint of something beyond our cosmic bubble, a shadow cast by another reality entirely. Not everyone's convinced. Skeptics argue the signal might stem from systematic errors in interpreting microwave data or unaccounted for phenomena like vast, undiscovered voids warping spacetime asymmetrically. Others propose it could be the imprint of a pre-Big Bang event, a cosmic defect frozen into the structure of reality during the universe's birth. But here's what keeps astronomers up at night. If the dark flow is real, it upends our understanding of the universe's fundamental architecture. We've long assumed the cosmos is isotropic, meaning it looks the same in all directions. The dark flow challenges that, suggesting an asymmetry on the grandest possible scale. It's as if we've spent centuries mapping a house, only to discover the walls are leaning because the entire building sits on a slope we never knew existed. Whether it's a multiverse, a cosmic bruise from an ancient collision, or something beyond our current physics, one thing's clear. The universe still has secrets written in ink we're only beginning to see. In the early 1970s, as radio telescopes swept the skies for the rhythmic pulses of distant neutron stars, one signal stood out not for its regularity, but for its strangeness. Hercules X1, a well-studied pulsar, had always behaved predictably, its X-ray flashes arriving like clockwork every 1.24 seconds. But then, without warning, its signal began to waver. The pulses didn't just weaken or scatter, they developed an odd, almost melodic modulation, as if something were bending the star's relentless rhythm into a cosmic whisper. For decades, this anomaly lingered in the data, dismissed by most as instrumental noise, yet a handful of researchers couldn't shake the feeling they'd stumbled onto something far more profound. What made Hercules X1's glitch so puzzling was its precision. Most pulsar irregularities stem from timing noise, random hiccups caused by the star's turbulent interior or magnetic field shifts. But this wasn't random. The modulation followed a distinct pattern, almost like a sine wave superimposed onto the pulsar's steady beat. One theory pointed to an unseen companion, a planet or another star warping the pulsar's signal as it orbited. The idea wasn't far-fetched. Astronomers had already theorized that pulsars could host planets, but calculations showed no plausible orbit that matched the signal's peculiar ebb and flow. Then came the wilder explanations. Could this be evidence of a starquake, a violent crustal shift on the neutron star's surface, sending ripples through its magnetic field? Or perhaps the pulsar was encountering dense pockets of interstellar plasma, bending its beams like light through a funhouse mirror. The most tantalizing and controversial suggestion came from a small group of physicists who wondered if the modulation wasn't natural at all. In 1975, a team at the University of Paris speculated that the pattern resembled intentional encoding, a concept that sent shockwaves through the scientific community. The idea was quickly shot down, but the seed had been planted. What if, just for a moment, we'd glimpsed something beyond natural astrophysics? Modern analysis has mostly settled the debate, sort of. Advanced simulations suggest the signal was likely caused by a combination of factors: minor starquakes coupled with instrumental artifacts from early X-ray detectors. Yet even today, some datasets from that era resist full explanation. Hercules X1's fluke remains a cautionary tale in astronomy, a reminder that the line between noise and discovery is razor-thin. Sometimes the universe's most intriguing messages aren't in the signals we decode, but in the ones that leave us forever wondering. The Cigar Galaxy, officially known as Messier 82, should be a cosmic wildfire, a place where stars are born so furiously their combined light outshines entire galaxies. But in 2009, astronomers detected something even wilder lurking in its chaotic core: bizarre radio emissions that shouldn't exist. Unlike the predictable wavelengths of star-forming gas, these signals pulsed with an irregular rhythm, flickering across frequencies like a radio dial stuck between stations. At first glance, they matched the signature of a microquasar, a small black hole devouring a star, but there was a problem. Messier 82 had no known black holes large enough to produce such intense bursts. So if not a black hole, what was cooking up these strange broadcasts? The galaxy's extreme environment only deepened the mystery. Messier 82 is a starburst galaxy, meaning it's birthing stars at a rate 10 times faster than our Milky Way. Supernova explode like fireworks, and stellar winds whip through space at millions of kilometers per hour. In this maelstrom, some argued the signals could be a new type of cosmic engine, perhaps colliding neutron stars or hypermagnetic stellar remnants. But the emissions refused to fit any known model. They were too sporadic, too broadband, almost as if they were artificial. That's when the whispers started. Could these radio waves be leakage from an advanced civilization? The idea wasn't entirely far-fetched. If a society had harnessed the energy of thousands of stars, their technology might produce waste emissions detectable across interstellar space. A handful of researchers even speculated about a Type 3 civilization, one capable of manipulating an entire galaxy's energy, though most dismissed this as science fiction. Yet nature, as always, had a few cards left to play. Further observations revealed tantalizing clues. The signals seemed to originate near dense clusters of young, massive stars, objects so hot and volatile, they might be capable of generating unprecedented magnetic phenomena. Some theorists now suggest these emissions come from mega-pulsars, neutron stars spinning at impossible speeds, wrapped in magnetic fields strong enough to twist spacetime itself. Others propose they're the echoes of dark matter annihilation, exotic particles colliding in the galaxy's core, releasing energy in ways we've never seen. One thing's certain, Messier 82's strange signals have rewritten the rules of astrophysics. Whether they're proof of extreme stellar physics, hidden black holes, or something even more extraordinary, they remind us that the universe's most baffling mysteries often lurk not in the voids but in the heart of the fire. Among the thousands of stars monitored by the Kepler Space Telescope, one stood out not just for its bizarre flickering, but for the radio whispers that seemed to answer back. KIC 552088, better known as the Kepler star, first made headlines in 2015 when astronomers noticed its light dipping erratically, sometimes by as much as 20%. Unlike Tabby's star's gradual dimming, these were sharp, jagged drops, as if something massive and irregular kept passing in front of it. But the real twist came when radio telescopes caught bursts of energy flaring from the same patch of sky, pulses that seemed to sync up with the star's strangest light patterns. It was as if the star wasn't just dimming, it was communicating. The radio bursts themselves were subtle, barely peaking above the cosmic background noise. Yet their timing was uncanny. When the Kepler star's light dipped most dramatically, the radio signals often flared, a correlation too precise to dismiss as coincidence. At first, researchers assumed they were seeing two unrelated phenomena, perhaps a dusty debris cloud blocking the star's light while a distant pulsar flickered in the same line of sight. But the more data they gathered, the shakier that explanation became. The radio bursts weren't coming from deep space. They originated close to the star itself, possibly within its immediate stellar neighborhood. That's when the interstellar gas theory took center stage. The Kepler star is a young, active sun, and like all stars, it's surrounded by a swirling magnetosphere, a web of charged particles and magnetic fields. Some astrophysicists speculate that dense pockets of interstellar gas might be drifting through this region, interacting with the star's plasma in ways that generate radio waves. Picture a rock tossed into a fast-moving river where the turbulence hits the rock's edges, whirlpools form. Similarly, as gas clouds plow through the star's magnetosphere, they could create shock waves that emit brief, intense radio spikes. But there's a wrinkle. These gas clouds would need to be colossal, far larger than typical interstellar structures, to produce radio bursts powerful enough for us to detect across hundreds of light years. Even stranger, they'd have to drift in front of the star at just the right angles to simultaneously dim its light and trigger radio emissions. The odds of such a perfect alignment seem vanishingly small, leading some to wonder if we're missing a key piece of the puzzle. One radical hypothesis suggests the star might be surrounded by an artificial megastructure, not a solid Dyson sphere, but a dynamic swarm of energy collectors or communication relays. These could distort the star's light while generating radio noise as a byproduct. It's a fringe idea, but the Kepler star's radio bursts do share eerie similarities with human satellite transmissions, narrowband pulses that flicker in and out of detectability. Then again, nature has a habit of outdoing our wildest imaginations. Recent simulations show that young stars like Kepler can harbor massive, unstable magnetic loops, think solar prominences on steroids capable of both dimming starlight and emitting coherent radio waves when they snap. Add a few rogue gas clouds into the mix, and you've got a recipe for the kind of synchronized weirdness we're seeing. For now, the Kepler star keeps its secrets. Every new observation adds complexity rather than clarity, turning what seemed like a simple case of interstellar weather into a full-blown cosmic whodunit. Whether it's gas dynamics gone wild, magnetic monstrosities, or something even more extraordinary, one thing's clear: this star isn't just flickering. It's performing, and the radio bursts might be its encore. Until we catch the act in full, we're left reading between the lines of light and static, piecing together a story written in the language of the unknown. In 2021, while sifting through radio telescope data from the Aquarius constellation, astronomers stumbled upon a signal so uncannily artificial sounding, it earned an affectionate nickname, the R2D2 signal. Unlike most cosmic static, this emission pulsed in a series of rapid, evenly spaced bursts, almost like a machine's heartbeat. The pattern was so precise, so deliberate-seeming, that for a fleeting moment researchers dared to wonder, had they just intercepted a message from the stars? The signal's rhythm was its most striking feature. It repeated every 1.3 seconds, a cadence so consistent it rivaled the precision of human-made radio beacons. Even more intriguing, the bursts weren't random noise, they clustered in groups of 5, a numerical quirk that sent SETI enthusiasts into overdrive. Could this be a counting sequence? A cosmic SOS, or just an extraordinary coincidence? The Discovery team quickly ruled out terrestrial interference. No satellites, military radars, or ground-based transmitters matched the signal's fingerprint. It was coming from deep space, some 3,000 light-years away, near a region brimming with young stars and turbulent gas clouds. But here's where nature flexed its ingenuity. Further analysis revealed the likely culprit, a pulsar, but not the ordinary kind. This one was enmeshed in a dense nebula, its usual radio pulses scattered and reshaped by swirling magnetic fields. Imagine a lighthouse beam passing through a frosted glass window. The light doesn't vanish, it fractures into new patterns. In this case, the nebula's turbulence was sculpting the pulsar's emissions into those eerily artificial-sounding clusters. It was a cosmic illusion, a trick of physics so perfect it fooled even seasoned astronomers. Yet the R2D2 signal refuses to fade into obscurity. For SETI researchers, it's a tantalizing case study, proof that the universe can mimic intelligence with breathtaking accuracy. If natural processes can produce signals this sophisticated, how many other messages might we have dismissed as noise? The signal also underscores a humbling truth: the line between natural and artificial isn't always clear. Until we fully understand the cosmos's acoustic palette, every odd pulse, every rhythmic whisper carries the faintest whisper of possibility. And that's why, even now, the R2D2 signal lingers in the archives, not as an answer, but as a reminder. Out there, in the static between the stars, the universe might just be waiting to surprise us again. When Oumuamua streaked through our solar system in 2017, it shattered expectations not just by being the first known interstellar visitor, but by the way it moved. Unlike any comet or asteroid we'd seen before, this strange, tumbling object accelerated as it raced away from the sun, defying the predictable pull of gravity. Scientists scrambled to explain the anomaly, proposing everything from outgassing, a comet-like release of trapped gases, to the far more speculative idea of an alien light sail. But one question lingered in the cosmic static. If Oumuamua was emitting something to propel itself, could those emissions have left echoes in the interstellar medium, rippling through nearby gas clouds like whispers in an echoing canyon? The possibility hinges on what exactly caused Oumuamua's acceleration. If it was outgassing, as many astronomers believe, the expelled hydrogen or water vapor would have dissipated quickly, but not before potentially interacting with the sparse gas drifting between stars. Picture a speedboat cutting through calm water. Even after the boat passes, the wake lingers. Similarly, charged particles or disturbed magnetic fields in Oumuamua's trail might have generated faint radio distortions in surrounding hydrogen clouds. These imprints would be vanishingly subtle but not undetectable, especially if telescopes were pointed in just the right direction at just the right time. Yet Oumuamua's sheer speed complicates the search. Traveling at nearly 92,000 kilometers per hour relative to the Sun, it crossed the orbits of multiple planets in mere weeks, leaving little opportunity to study its wake before it vanished into the void. By the time astronomers realized its trajectory was anomalous, the object was already too distant for detailed observation. Any signals it might have left in nearby gas clouds would have been stretched thin by the vastness of space, diluted into the background noise of the cosmos. That hasn't stopped researchers from speculating. Some argue that if Oumuamua's acceleration stemmed from something more exotic, like the pressure of sunlight on a thin, reflective surface, the disturbance to interstellar gas would have been far stranger. A light sail, for instance, wouldn't expel material. Instead, its passage might have polarized tiny dust grains or left ultrafine plasma ripples in its wake. These effects would be even fainter than outgassing traces, but they'd also be more distinct from natural phenomena, like a fingerprint on glass. The irony. Even if Oumuamua did leave detectable signals, we might have missed them entirely. Most radio telescopes aren't trained on random patches of interstellar gas unless there's a known reason to look. And without knowing Oumuamua's exact composition or the mechanism behind its acceleration, astronomers can't retroactively predict where or how its echoes might have appeared. It's like trying to reconstruct a lightning strike days after the storm has passed. The evidence is there, but scattered to the wind. What makes Oumuamua's case so tantalizing isn't just the unanswered questions, it's the potential blueprint it offers for future discoveries. If another interstellar object arrives, we'll be ready. New telescopes like the Vera Rubin Observatory could spot such visitors earlier, giving scientists time to hunt for any signals they imprint on the galactic medium. And next time, we might just catch the echoes before they fade, proof that even silent travelers like Oumuamua can still speak volumes if we're listening closely enough. Deep in the cosmic map lies a place so empty it defies logic. The Boötes void, a spherical region of space spanning 330 million light-years where galaxies are almost entirely absent. If the Milky Way sat at its center, we wouldn't have known other galaxies existed until the 1960s. Yet within this staggering nothingness, radio telescopes have picked up something impossible: whispers. Not the usual cosmic static, but ultra-faint signals drifting through the void like echoes from a forgotten corner of the universe. What makes these signals so baffling isn't just their existence, it's what they imply. In a region this empty, there's almost nothing to generate radio waves. No bustling star clusters, no colliding galaxies, not even enough free-floating gas to spark a detectable emission. So when faint but coherent pulses were first detected in 2019, astronomers faced a paradox. The signals were too structured to be random noise, yet too weak to originate from any visible source beyond the void. One theory points to dark matter not as an inert shadow, but as an active participant in cosmic physics. Certain dark matter models predict particles could decay or collide, releasing energy as faint radio waves. If true, the Boötes void might be the perfect dark matter laboratory, its emptiness amplifying signals that would drown in the noise of a galaxy-rich environment. Then there's the primordial gas hypothesis. The Boötes void isn't a perfect vacuum. It contains traces of hydrogen left over from the Big Bang, so diffuse it's practically invisible. But under rare conditions, this gas could theoretically collapse into faint, transient structures, emitting radio waves as it interacts with cosmic background radiation. Picture a shallow pond on a windy day. While most ripples cancel each other out occasionally, a few align just right to create a visible wave. Similarly, these whispers might be the rare moments when primordial hydrogen rings in the void's silence. But the most unsettling possibility, the signals aren't coming from the void at all. Gravitational lensing, the bending of light by massive objects, could distort signals from distant galaxies, warping and magnifying them into apparent nothingness. It's like hearing a voice echo through a cave and assuming it originates from the walls, when in reality, the sound traveled miles underground before reaching you. If lensing is at play, the Boötes void might be a cosmic ventriloquist throwing its voice from unseen corners of the universe, yet every explanation leaves gaps. Dark matter interactions should produce predictable signal patterns, but these whispers flicker unpredictably. Primordial gas would need impossibly dense pockets to emit detectable waves, and lensing can't account for the signal's peculiar spectral shapes. The Boötes void's mysteries remind us that emptiness isn't passive. It's a canvas for the universe's strangest physics. Whether it's dark matter murmuring, ancient gas stirring, or something entirely unknown, one thing's clear: even silence in the cosmos speaks volumes. Somewhere in the constellation Cygnus, hidden behind veils of interstellar dust, a cosmic predator lurks, and it's broadcasting. Cygnus X3 isn't your average black hole or neutron star. It's a microquasar, a scaled-down version of the supermassive monsters that power distant galaxies, and it's been spitting out some of the most erratic X-ray and radio signals ever recorded. What makes this system so mesmerizing isn't just its violence, it's the way its outbursts seem to dance to a rhythm no one can decipher, as if the gas clouds around it are whispering secrets into the void. At the heart of Cygnus X3 lies a compact object, likely a black hole or neutron star, locked in a lethal embrace with a companion star. As it devours its partner's gas, the system erupts in bursts of high-energy radiation, flickering like a candle in a storm. But here's the twist: these aren't random explosions. The X-ray flares follow rough cycles, flaring up every 4.8 hours like clockwork, only to suddenly shift tempo without warning. Radio observations add another layer of strangeness. Sometimes the emissions pulse in steady, predictable waves. Other times they erupt in chaotic static, as if the system can't decide whether it's a metronome or a thunderstorm. The leading theory blames the environment. Cygnus X3 is buried in one of the Milky Way's densest stellar nurseries, a region choked with gas and dust. Some researchers argue that passing clouds could be distorting the signals. Imagine trying to hear a song played through a wall of shifting fog. As gas drifts between us and the microquasar, it might absorb certain wavelengths or magnify others, creating the illusion of erratic behavior. There's even evidence that the companion star's stellar wind, a stream of charged particles, could be colliding with these gas clouds, generating shockwaves that further scramble the signals. But not everyone's convinced. A rival camp points to the compact object itself. If the black hole or neutron star has a wobbly accretion disk, a swirling ring of doomed matter, its precession could explain the timing shift. Picture a spinning top that starts to tilt. As the disk wobbles, its jets of radiation might sweep across Earth's line of sight at irregular intervals, creating the illusion of a capricious signal. Even wilder, some models suggest Cygnus X3's companion star might be dumping gas onto the compact object in clumps, like a poorly tuned faucet, leading to sporadic outbursts. Then there's the wild card. What if we're seeing two phenomena at once? radio telescopes have caught hints that Cygnus X3's jets, the high-speed particle beams fired from its poles, might be plowing through nearby gas clouds, creating turbulence that backfeeds into the system. This could set up a feedback loop where the environment distorts the signals, and the distorted signals, in turn, reshape the environment. It's a cosmic Ouroboros, a snake eating its own tail. One thing certain, Cygnus X3 refuses to fit into a neat box. Whether it's gas clouds playing cosmic telephone, a wobbly disk throwing off the rhythm, or some undiscovered physics lurking in the chaos, this microquasar is a reminder that even the universe's loudest voices can be hard to interpret. And that's what makes it so irresistible. Every flicker, every burst, every silent pause is a clue not just to how this one system works, but to the untold stories of other monsters hiding in the galactic dark. Deep in the heart of the Perseus cluster, a sprawling metropolis of galaxies 240 million light-years away, there's a hum. Not the random static of cosmic noise, but a deep, resonant vibration, a bass note thrumming at frequencies 1,000,000 times lower than human hearing. Detected in 2003 by NASA's Chandra X-ray Observatory, this eerie drone isn't just background music. It's a tremor rippling through the very fabric of the cluster, carrying secrets about the universe's largest structures and the monsters that may be stirring them. The Perseus hum pulses at a frequency of 1 oscillation every 10 million years, a rhythm so slow it can only be traced by studying the ripples it leaves in the cluster's seething intergalactic gas. Picture dropping a stone into a pond. The waves spread outward, distorting the surface. Here, the stone is something far more violent, supermassive black holes, likely the one anchoring the cluster's central galaxy, NGC 1277. As these black holes devour matter, they don't dine quietly. Jets of plasma blast from their poles at near light speed, punching into surrounding gas like a cosmic jackhammer. The resulting shockwaves reverberate through the cluster, setting the entire cloud of gas vibrating like a struck bell. But there's a twist. The hum isn't uniform, it's layered, with multiple frequencies overlapping like chords in a song. That complexity has led some researchers to propose an even wilder origin. What if the sound isn't just from black hole jets, but from the cluster's gas itself? The Perseus cluster is threaded with magnetic fields, and some models suggest these fields could act like guitar strings, vibrating as charged particles whirl through them. If true, the hum would be a hybrid, part black hole bellow, part celestial symphony. The implications reach far beyond Perseus. Galaxy clusters are the universe's largest gravitationally bound structures, connected by the cosmic web, a vast network of gas and dark matter filaments. The hum offers a rare opportunity to study this web's acoustics. Just as earthquake tremors reveal Earth's inner structure, these vibrations could map the density and temperature of intercluster gas with unprecedented precision. Already, astronomers have used the hum to estimate the cluster's total mass, including its invisible dark matter halo, yet mysteries remain. Why does the hum persist so steadily when black hole activity is notoriously erratic? Could there be other sources, like primordial gravitational waves from the Big Bang, contributing to the drone? And most tantalizing, if we listen closely enough, could similar hums be detected in other clusters, each with its own cosmic fingerprint? The Perseus hum is more than a curiosity. It's a new language for decoding the universe's architecture, one low-frequency whisper at a time. And as our telescopes grow more sensitive, we might just find the cosmos is full of such vibrations, a chorus too deep for our ears but not for our ingenuity. Back in 1967, a young graduate student named Jocelyn Bell Burnell was scanning the skies for cosmic radio waves when she stumbled upon something extraordinary, a signal so precise, so unnaturally rhythmic, it seemed to defy the chaos of the universe. Pulses arrived every 1.337 seconds with clockwork regularity, like a metronome ticking in the void. The discovery, later named LGM-1 short for Little Green Men, sent shockwaves through the astronomy community. For a brief, electrifying moment, the world dared to wonder, had we just intercepted a beacon from an alien civilization? The truth, when it came, was both humbling and revolutionary. LGM-1 wasn't a message, it was the first documented pulsar, a rapidly spinning neutron star blasting beams of radiation into space with each rotation. But here's what's often overlooked: those perfectly timed pulses almost didn't get discovered. The signal was so clean, so artificial seeming, that Bell Burnell's advisor, Anthony Hewish, initially dismissed it as terrestrial interference. It took months of meticulous observation to confirm its cosmic origin, and that raises a chilling question. How many other LGM signals have we written off as noise, only to miss the universe whispering its secrets? Fast forward to today, and astronomers are revisiting that pivotal moment with fresh eyes. New research suggests interstellar gas clouds, those same wispy veils of hydrogen and helium drifting between the stars, might be capable of mimicking pulsar-like signals under rare conditions. Picture a vast cosmic lens. When radio waves pass through dense magnetized gas clouds, they can become distorted, scattered, or even reshaped into artificial-looking pulses. Turbulence within these clouds might briefly focus radio emissions into narrow beams, creating the illusion of a rhythmic broadcast. It's like sunlight flickering through swaying tree branches. The light isn't pulsing, but the pattern emerges from the movement of the obscuring material. Even more intriguing are the echoes. Some gas clouds act as celestial repeaters, bouncing signals back in delayed, degraded copies. A single natural radio burst, say, from a flaring star could bounce between multiple clouds, arriving at Earth as a sequence of evenly spaced pulses. To an observer, it might look exactly like a deliberate transmission. In fact, a 2022 study simulated this exact scenario, proving that under the right conditions, gas clouds could produce signals virtually indistinguishable from early pulsar detections. The universe, it seems, is a master illusionist weaving mimicry into the fabric of space itself. So where does that leave the search for extraterrestrial intelligence? The lesson of LGM-1 isn't just about what we found, it's about how easily we could have missed it, or worse, mistaken it for something mundane. Every odd signal, every flicker of cosmic static carries the ghost of that possibility. And with gas clouds now known to stage their own interstellar puppet shows, the line between natural and artificial grows blurrier than ever. Perhaps the real message of LGM-1 isn't in the pulses themselves, but in the humility they demand. The universe speaks in riddles, and sometimes the most artificial-seeming whispers are just nature's way of reminding us we're still learning to listen. Hoag's object is the kind of galaxy that makes astronomers do a double take, not just because it looks like a cosmic bullseye, but because it's whispering something strange in radio waves. Most galaxies are chaotic whirlpools of stars and gas, but Hoag's object is eerily symmetrical, a perfect golden ring of young, blue stars encircling an ancient yellow core with a vast, almost empty gap between them. It's as if someone took a spiral galaxy and stretched it into a halo, leaving astronomers scratching their heads for decades over how such a structure could form. But the real enigma isn't just its shape, it's the peculiar radio emissions crackling from its depths, signals that refuse to match any known cosmic blueprint. The first oddity lies in the ring itself. When radio telescopes like the Very Large Array zoom in, they detect faint but persistent emissions threading through the star-forming region's energy that shouldn't exist in such a pristine, isolated ring. Normally, radio waves from galaxies come from supernova remnants or frenetic stellar nurseries, but Hoag's object signals are too uniform, too spread out, as if the entire ring is humming with low-level energy. One theory suggests the galaxy's unusual structure might be to blame. Unlike spiral galaxies where gas is constantly stirred by rotating arms, Hoag's object's ring is eerily stable, a closed loop where gas could accumulate and interact in ways we've never seen. Picture water swirling in a perfect circle, no turbulence, no ripples until suddenly, subtle vibrations start resonating through the entire system. Then there's the core. Nestled inside the ring, the ancient central bulge glows faintly in radio waves, a quiet murmur compared to the ring's activity. But here's the puzzle: the two shouldn't be connected. In most galaxies, the core and the disk interact through gravity or magnetic fields, but Hoag's object's gap is so vast, tens of thousands of light years of near nothingness, that traditional physics struggles to explain how they're communicating. Yet the radio emissions suggest they are. Some researchers propose hidden bridges of cold, dark gas, invisible to optical telescopes but capable of conducting energy like cosmic wires. Others wonder if the galaxy's past holds the key. Perhaps a long-ago collision sent shockwaves through the gas, leaving behind a latent echo still vibrating today. The wild card: Hoag's object isn't alone. A handful of other ring galaxies show similar radio oddities, hinting that these perfect circles might be cosmic tuning forks, resonating at frequencies we're only beginning to detect. Whether it's the ghostly fingerprints of a violent merger, the hum of exotic magnetic fields, or something even stranger, one thing's clear: Hoag's object isn't just a pretty anomaly. It's a signal in the dark, a reminder that even the most serene corners of the universe might be hiding a pulse we don't yet understand. And every time we listen, it asks us to rethink what we know about the music of the cosmos. In 2022, astronomers scanning the Triangulum galaxy, our neighbor 2.7 million light-years away, caught a signal that shouldn't exist. Nestled in the outer spiral arms of Messier 33, this anomaly pulsed at a steady 4.7 GHz, a frequency typically reserved for human satellite communications here on Earth. At first glance, it looked almost technological: narrowband, persistent, and eerily reminiscent of the kind of leakage our own civilization leaks into space. But the Triangulum anomaly wasn't coming from Earth. It was coming from a region of M33 with no known pulsars, no active black holes, not even a visible star cluster to explain it. It was as if the galaxy itself had flicked on a radio and no one could find the switch. What made this signal so baffling wasn't just its isolation, it was its spectral fingerprint. Most cosmic radio emissions scatter across a range of frequencies, blurred by magnetic fields or Doppler shifts, but this was laser-sharp, barely wavering over weeks of observation. Natural processes rarely produce such precision. Even pulsars, the universe's most reliable metronomes, exhibit subtle drifts as they spin. The Triangulum anomaly, by contrast, held its frequency like a dialed-in transmitter. SETI researchers immediately took notice. Could this be a technosignature, the radio equivalent of a cosmic "we're here, yet nature loves a good curveball"? One compelling theory involves an undiscovered type of maser, a naturally occurring radio amplifier where molecules in space, like water or methanol, get pumped by starlight into emitting coherent beams of radiation. Most space masers are messy, their signals smeared across frequencies, but under extreme conditions, say in a dense, magnetized gas cloud near an invisible protostar, the emissions might focus into something unnervingly artificial-looking. Picture sunlight hitting a perfectly shaped dewdrop. For a moment, it becomes a focused beam. Similarly, the Triangulum anomaly could be a cosmic lensing effect, a rare alignment turning a faint whisper into a shout. Then there's the dark horse explanation, a false wake. In 2021, astronomers realized that passing interstellar gas clouds can sometimes reflect human-made radio noise back into space, creating echoes that appear to originate far beyond our solar system. Could the Triangulum anomaly be Earth's own signals bouncing off an unseen dust cloud near M33? The math almost works except for one hitch. The signal's frequency doesn't match any known terrestrial broadcasts, and its 4.7 GHz line is suspiciously quiet in human usage. It's like hearing a recording of your voice saying words you never spoke. As always, the most thrilling possibilities linger just beyond reach. If the signal isn't natural and isn't ours, what's left? A civilization in M33 would need staggering power to broadcast a detectable signal across intergalactic space. Think harnessing the energy of a star. But here's the twist, they wouldn't need to aim it at us. Our omnidirectional beacon, meant for local communication, might still leak enough energy to be caught by our telescopes as a faint blip. Or perhaps it's not a message at all, but the byproduct of megascale engineering, a Dyson swarm's waste heat, or a particle accelerator the size of a solar system. For now, the triangulum anomaly remains unresolved. Follow-up observations have yet to detect a repeat, leaving astronomers with a single, tantalizing data point. But its legacy is undeniable, a reminder that even our nearest galactic neighbors can harbor signals that defy categorization. Whether it's a new astrophysical phenomenon, a cosmic mirror reflecting our own noise, or something more profound, one thing's certain: the universe keeps a few frequencies reserved for surprises. And M33 just reminded us to keep listening. At the heart of our galaxy, where stars swarm like fireflies around an invisible giant, something strange keeps crackling over the radio waves. Sagittarius A, the supermassive black hole anchoring the Milky Way, isn't just a silent predator. It's surrounded by bursts of radio energy that flicker like Morse code from the abyss. These aren't the predictable pulses of a pulsar or the chaotic static of stellar nurseries. They're sharp, irregular eruptions, sometimes spaced hours apart, other times clustering in frantic volleys. And astronomers are locked in a heated debate. Are these bursts the death throes of gas clouds spiraling into oblivion, or is the black hole itself somehow generating this eerie static? The gas cloud theory paints a vivid picture. Imagine vast tendrils of hydrogen, some as massive as entire solar systems, drifting too close to Sagittarius A's gravitational grip. As they're stretched and shredded by tidal forces, their molecules collide, ionize, and release torrents of radio waves in their death spiral. This spaghettification process could explain the burst's chaotic timing, each flare marking another cosmic snack for the black hole. Supporting this, the Atacama Large Millimeter Array has spotted ghostly wisps of gas near the galactic center, their distorted shapes hinting at violent interactions with unseen forces. But there's a problem. Some bursts arrive with energies that gas cloud collisions struggle to explain: short, intense spikes resembling the lightning discharges observed in Earth's thunderstorms, but scaled up to cosmic proportions. That's where the black hole's own machinery comes into play. Sagittarius A isn't just a vacuum cleaner, it's a dynamo. Its accretion disk, the swirling ring of superheated gas orbiting the event horizon, is laced with magnetic fields trillions of times stronger than Earth. When these fields twist and snap, they could launch jets of particles that interact with surrounding plasma, creating shockwaves detectable as radio bursts. It's like the crackle of a downed power line, only spanning light years. The plot thickens with the burst's peculiar patterns. In 2021, researchers noticed that certain flare sequences echoed. Weak bursts often preceded stronger ones by consistent intervals, as if the system were loading energy before releasing it. This behavior mirrors earthquake aftershocks or even human-made electrical grids surging before a blackout. Such ordered complexity suggests underlying physics we're only beginning to grasp, possibly involving resonance in the black hole's magnetosphere or instabilities in its feeding cycle. Then there's the wild card, sterile neutrinos. A minority of theorists propose these hypothetical particles, produced in the black hole's extreme environment, might decay radioactively as they stream outward, leaving behind fleeting radio signatures. It's a long shot, but if proven, it would revolutionize particle physics and cosmology simultaneously. What makes these bursts so mesmerizing isn't just their origin, it's what they reveal about the galactic center's ecosystem. Each flicker is a breadcrumb leading us deeper into the chaos around Sagittarius A, where gravity, magnetism, and plasma physics collide in ways unseen anywhere else in the universe. Whether they're the screams of dying gas clouds, the groans of a black hole's magnetic field, or something even more exotic, one thing's certain: the heart of our galaxy is anything but silent. It's a storm we're only beginning to tune into, one burst at a time. Tabby's star refuses to fade into obscurity. Years after its bizarre, dimming patterns first captivated astronomers, new observations have deepened the mystery, and interstellar gas clouds might hold the key. Recent data from the James Webb Space Telescope reveals something startling. The star's light isn't just being blocked, it's being scattered. When scientists analyzed the wavelengths of light passing through whatever's obscuring the star, they found telltale fingerprints of finely structured dust, particles too small and evenly distributed to be ordinary debris. This isn't the chaotic rubble of a planetary collision or the jagged fragments of a shattered moon. It's more like a cosmic veil woven from particles barely larger than smoke, and that's where the gas clouds come in. Interstellar gas isn't just floating passively between the stars. Under the right conditions, it can clump into intricate formations, trapping dust in magnetic tendrils or electrostatic webs. Some theorists now suggest that vast, wandering clouds of this ionized gas might be drifting through Tabby's star's system, their invisible fingers shaping the dust into transient screens. Imagine a breeze organizing sand into ripples, except here, the breeze is the galaxy's own magnetic field, and the sand is starlight stealing dust. These clouds could explain why the dimming isn't periodic. They're not orbiting the star in neat cycles, but passing through haphazardly, like interstellar weather fronts. Yet even this elegant theory frays at the edges. For one, the dust around Tabby's star is too hot, warmer than typical interstellar grain should be at that distance from a star. That's led to a radical counter-proposal. What if the dust isn't from a gas cloud at all, but the remnants of a dying comet swarm? If the star recently devoured a family of icy bodies, their evaporated guts could have left behind a glowing shroud of superheated nanoparticles. But that raises another question. Why haven't we seen similar dimming around other stars? The universe isn't short on comet carnage, yet Tabby's star remains an outlier. The most tantalizing clue lies in the star's radio emissions. Last year, the Very Large Array detected faint but structured radio waves coming from the same direction. Not the blast of a natural cosmic storm, but a murmur, almost like the hum of machinery. Gas-cloud interactions can produce radio noise, but this signal had a curious fingerprint. It pulsed weakly in sync with some of the star's deepest dimming events. Coincidence, maybe, but it's enough to make even skeptics wonder if we're seeing more than just gas and dust. Could there be structures, natural or otherwise, harnessing these clouds, using them like cosmic sails or shields? The answer might lie in the data we don't have yet. Upcoming missions like the European Space Agency's Pluto telescope will monitor Tabby's star with unprecedented precision, hunting for patterns too subtle for current instruments to catch. Meanwhile, laboratory experiments are simulating how interstellar gas and dust interact under extreme conditions, testing whether they really could form the kinds of light-scattering veils we're seeing. Every new observation peels back another layer, revealing not just the secrets of one strange star, but the hidden choreography of the galaxy itself. One thing's certain, Tabby's star isn't done surprising us. Whether it's gas clouds sculpting dust into celestial theater curtains, the aftermath of a cosmic feeding frenzy, or something even more extraordinary, the next chapter of this mystery might rewrite our understanding of how stars and the space between them interact. And when the next big dimming event hits, because it will be watching closer than ever, ready this time to catch the universe in the act. From the haunting pulse of the wow signal to the rhythmic whispers of the chime repeater, these 25 cosmic enigmas reveal a universe far stranger than we ever imagined, and interstellar gas clouds are the silent conductors of this celestial symphony. They bend signals like prisms, amplify whispers into shouts, and scatter messages we're only beginning to decode. Every flicker, every burst, every unexplained pattern is a reminder the space between the stars isn't empty. It's alive with unseen forces, hidden structures, and maybe, just maybe, echoes of intelligence beyond our own. Think of these gas clouds as cosmic detectives, best witnesses and worst liars. They distort signals just enough to make natural phenomena seem artificial, and artificial ones seem natural. The same clouds that might have camouflaged the wow signal could be magnifying faint whispers from civilizations we've yet to discover. They're the universe's hall of mirrors, reflecting riddles back at us with infinite variations. But here's the exhilarating part: we're just getting started. Every new telescope, every algorithm, every night spent staring at the data brings us closer to unraveling these mysteries. Maybe the next signal will be the one that changes everything. Or maybe it'll be another beautiful dead end, a cosmic joke reminding us how much we still don't know. That's the thrill of the hunt, so stay curious. The universe isn't done talking, and we're only beginning to listen. Hit subscribe to join us as we chase down the next great cosmic whisper. Because in a galaxy where gas clouds hide more secrets than black holes, the next big discovery could be just one signal away. Drop your favorite mystery in the comments below. Was it Tabby's star's flickers, the Lorimer Burst scream, or something we haven't even found yet? The conversation doesn't end here. The stars are waiting.